status? Ele dá um F5 aqui, ó.
Obrigado, Luis. Okay, so yeah. Are we all here? Ricardo Aguiar, is he downstairs?
Rodrigo?
Rodrigo.
Isso.
Okay. Who else? Who? Leandro is coming. Okay. Okay, so I'll try not to erase and we start here. Okay, so the paper of Zoologicov is kind of huge. So we are going to try to study one corner of it, and our goal would be to study the ON model with n bigger or equal than 3. So let's suppose we have the following model, where we have some coupling. I forgot how he calls it, but this would be a convention that people that do string theory would like to use, but doesn't matter, some constant here. And then an integral over space and time of the derivative of a vector n squared, where n is on the unit sphere. So we can put a Lagrange multiplier forcing n squared to be 1. So this would be the action for my model. It's just a bunch of scalars. N is n1 up to n capital N. And we just have, if it was not for the second term, it would be n 3 master scalars. But because of the last term, it's n scalars with one constraint, so this would be points on a scale. Okay? And so the question is, I have this theory. What would an experimentalist see? If I do an experiment and I send many particles with momentum P1, P2, P3, and P4. That's my experiment. And then the question is, what do I get? And what are these amplitudes for this process? Okay? So this would be the question that we would like to make a prediction for our experimentalist friend. Okay? What are these amplitudes, and what are the possible final states, and what are the amplitudes? Okay? Any question here? So the very first comment that Zoologicov is reviewing is the statement that for the final states, if I call this Q1, Q2, Qm, that the final states actually, the set of Q1 up to Qm, needs to be equal to the set of the initial momenta P1 up to Pn. And this is a consequence, this is implied by the existence of many conservation laws. So in the same way that when you scatter two particles, if you conserve momentum and energy, the scattering is elastic, and the final and initial momentum are the same. For more than two, that's not obvious, and in general it's not true. But if you have more conservation, if it's not just energy and momentum, then it will be true. The initial and final set need to be the same. So that's already very special, In particular, you see that it implies that this m needs to be equal to n, and that the momenta need to be the same. Of course, they could be permuters. Maybe you get P1, P3, P2, goes to P1, P2, P3, but the set needs to be the same. And this leads to a picture that these amplitudes, when these charges exist, that these amplitudes, that leads to the answer to the second question, these amplitudes can be thought of as a sequence of two-body scattering processes. In this case, for example, that I scatter 4 particles, I could draw something like this and say that my amplitude is a product of 2 to 2 scattering events. And so in this case, for example, my amplitude would be a product of these objects that are called the 2 to 2 S matrix. And how many there will be? 1, 2, 3, 4, 5, 6. And in general, it's all possible encounters of the particles. There will be some number here. That would be something like n times n minus 1 over 2, something like that. When n is 4, this gives 6, which is correct. And so that's his proposal, that there are theories that have many charges for which the amplitude, you can think of it like this. You just move these lines so that this one happens, then 1 year later this happens, then 2 years later this happens, and so on. Then if they happen very separated in time, of course I just multiply the 2 to 2 scattering amplitudes. And that gives the result. And so this gives the result. Of course I can move the lines differently to separate them. And therefore there are consistencies. This can only work if you have the Young-Baxter or factorization equations. Namely, that if I multiply an S matrix like this must be equal to this process. I can move this line. I went from this picture to this picture by moving this line. Oops. In this picture, I move this line in this direction. Made it cross that line, and I got to this picture. And so this tells me that our amplitude is a product of 2 to 2 amplitudes, where these 2 to 2 amplitudes, they are matrices, right? So I have index I and j producing index k and l. So it's really a matrix at each point. And this matrix obeys cubic-like equations of the type S equal S. And I'm being schematic because we are going to be rigorous in a few seconds. And so, that's basically it. If you want to compute this amplitude, all you need to compute to answer this question, therefore, is this object here. So this S with indices I, j, k, l is all we need. Okay. Now this applies to many theories that for which these extra charges exist, and it applies to this theory. Why? Well, that's not in the paper. That is some other work that other people did, checking that you could, for this model, construct analog of energy and momentum with many more charges. So that's background. So this he doesn't prove. That's not the subject of the paper. This is assumption. The only thing we know is that it's the model, it has extra charges. This is saying the model is integral. So this is not here. Once we know that these charges are there, the only way a set of momenta is conserved is if the sequences are effectively pairwise, because in each pairwise scattering they are just swapped, the momentum. And so that's the simplest way of making sure that the momentum are conserved. So it's clear that this implies this. The fact that this implies this, right? This way is trivial. This way is a little bit less trivial, but it's also possible to do. But he doesn't do, and we are not going to do. But basically, of course, This implies this, that's easy. This also implies this. It's a bit harder, but it's possible to do.
So you, in the other way around, it's classical pyramid.
Right, so here we assume it's classical, but we assume it survives the quantization. So we assume these charges exist at the quantum level, and we are going to solve. Okay, any question?
So, it seems here that we are implicitly assuming that the three body interactions are not present, and I cannot see where it's given.
If there was a genuine three-body interaction, there is zero chance that a set of momenta would be conserved. Because if you send three particles and they really meet in a three-body way, why would the three momenta be the same? All that would be conserved is the energy and momentum. There's the probability that... So the fact that the set of momenta is conserved is very natural, that they need to be effectively pointwise.
Okay.
So even when you prepare wave packets and they are prepared to meet exactly at a point, we know this must be equivalent to separating them and letting them meet in a very chronologically distinct way. Okay. Now we have this model. What are the indices I and j? What should be I and j? And I want to stress that this is a very non-trivial question. It's hard. What is I and j? What would you say? What is I and j? What are the values that I can take? Here, I and j, etc. They take what values? Say from 1 to what?
I would say n. The number of particles.
No. This is a 2 to 2 S matrix. This describes this S matrix. Or this with index I, j, k, l. So it's only about 2 particles. So what are the indices of this incoming and outgoing indices? 2 incoming, 2 outgoing. What values should it take?
The number of species.
The number of particles, the type of particle that goes from n. N is true, but it's non-trivial if you think a bit about it. It's not obvious that the number of particles is n, and not always it's obvious. If I replace this model, for example, let me show you another integrable model that you could write. Okay, now let me just not do it. But why is it n? You see, this model is not weakly coupled. It's a strongly coupled model. If we try to write, let's write the equations of motion for this model. And the equations of motion are what? It's box or Laplacian of n is equal to Lagrange multiplier times n. Do you agree? I just derived the equation of motion. And now dot this with n to get that n dot box of n equal to lambda, because n squared is 1. Using that n squared is 1 and taking 2 derivatives of n squared is 1, you can show that this left hand side is nothing but minus the derivative of n squared. That comes from 2 derivatives on n dot n equal 1. And therefore the equations of motion for this model is box of n plus del n square n equals 0. So you see there's no free parameter, there's no weak coupling limit, you just have some nonlinear equations that a priori you have to solve. There's no simple notion of what's a particle and, as a free excitation. So why do we say right away n? Where did this idea that it's n came from? Right? It's non-trivial. So I could write other models that are strongly coupled. For example, another model that's very well known that you could study with similar techniques to the ones we are going to study, so-called the principal chiral field. And the principal chiral field would be the same integral over time and space. And instead of, and now it will be the trace of a derivative of a group element G times the derivative of the group element G minus 1. Okay, just take this, where G is a group element now. Now G is an element of SUN. So this is very similar to trace of F squared in an unabelian gauge theory. And now I ask you here, what are the particles in this theory? Right? What are the particles here? I runs from 1 to what? This one is very hard actually. It's hard. So
N minus 1.
no. It's complicated. Okay, so how can we try to? I'm not trying to say the answer, but it's complicated. We have to understand what are the particles. What is a particle? It transforms in some irreducible representation of SUN in this case, or of SON in this case. But which representation? How do we know? How do you know that a particle is not a traceless symmetric tensor of SON? Could be. The theory is strongly coupled. How do we know what are the effective low energy dynamics? We don't know. We just know that because the theory has this symmetry, the particles better transform correctly under the symmetry, but they can transform in any representation a priori. Right? They could be singlets. They could confine and form singlets. Maybe there is one particle only that's stable. Right? So many things that could happen.
So in this model, how do you know what's the particle?
So how can we know in this one, right? How can we get the hint about this question of where the index goes? And one answer is large N. We learned large N in the last lecture, so we could try to study the model at large N to get some intuition. So let's do it. So the idea is the following. Is that, let's suppose I have this model, and I have my path integral. And you see that n appears quadratically. So because n appears quadratically, I can integrate it out. Right? So I can write this as a path integral over lambda. And then what do you get when you integrate out n? When you integrate out n? Imagine n was a single scalar. What would you get if it was just a single scalar? When you integrate out something quadratic, what do you get? Sorry? Sorry, you integrate something quadratic, you get what? Oh yeah?
It's 1 over the determinant of some operator.
1 over the determinant is almost correct. When you integrate something quadratic, we get
The square root of
1 over square root of the determinant, right? So exponential of minus square root, so 1/2 of the determinant. Determinant means trace of logarithm of the operator del square, maybe with a minus, plus lambda. Do you agree? This trace log is the same as determinant downstairs with square root. And I left some space here. What should I put here? Let me help a little bit. Let me continue just writing something. And then there is the other term that is left there, minus the integral of lambda times some coupling.
So the coupling is missing, right?
No, the coupling is okay. It will just multiply this and it will get out of the log. It will just be a constant. It's not important. What? But something important is missing. Factor of n. That's super important because we integrated out n scalars. So n. And it's this n that's crucial because now we can use saddle point because n is very big here. And that's why it's very important that n is large. And so because n is large, we can extremize this section with respect to several points. Only the classical configuration matters. And when we extremize delta of this effective action, delta lambda equals 0, that will give some critical value on the start. It will tell me that this Lagrange multiplier wants to go to some fixed background. So the physics is that the Lagrange multiplier at large n freezes and goes to some value plus some fluctuation. But to understand the physics, we focus on this constant value. Right? Right? And so now, you see, now we learn that at large n, this is more or less a constant. But if this is more or less a constant, what's this action? It's just n free scalars, massive, where the mass is the value of the constant. Okay, good. So we learn that we have n particles of mass square root of lambda star. So that's good. So that should work if n is 10 or 12. Does it work if n is 3 or 4? Well, let's hope it does. But at least qualitatively we learned that large n tells us this. That they are vectors and that there are n particles. That was not obvious. And well, it's one line, so it's almost obvious, but it required some work. Okay. So now we are studying, so where are we? We want to find an S matrix. I, J goes to K, L. The picture again is that I have I and J, my type of particles, with momentum P1 and P2. And it goes to, say, L and K, with momentum that's conserved, so this is also P2 and this is also P1. Because energy and momentum is conserved, so if this is P1 and P2, that is P2, P1 and P2.
So it's very hypothetical, but if we had got an answer that was like n times n minus 1 over 2.
Here?
So, yeah, in some other model, then we would think that there's like an anti-symmetric representation for independent particles. But then the symmetric and anti-symmetric representations have almost the same dimension of large n because they're both n squared over 2. So this argument would be enough in those cases.
I don't know of other examples. I only know one more example where this large n works very well. Because, for example, suppose I take this model and ask what do I learn from large n? And the answer is nothing, because when G is a matrix, like here, large n is not that powerful. We saw in Witten's lecture, right? We could draw cartoons and so on. We could not compute things. We still need to sum over all planar diagrams and so on. This one is special because we did large n in a vector model. And vector models are easy, are much easier. See, large n was one line. Witten's large n was one lecture. So vector models are trivial, and large n is trivial, and you always find this conclusion that there are n particles. And matrix models are hard, and you can do large n, but it doesn't help you much. So for example, here the answer is that a particle, here you can say a particle transforms in the vector of SOM, right? And here a particle transforms into the product of some representation on the right and the same representation on the left. That's very non-trivial. And so a particle comes with an extra index saying how many boxes you have here, and the full Hilbert space becomes the sum over all this n, and it's complicated. And it's very hard to guess it from large n. I don't know exactly how to guess it.
Okay, so there are integral models where the particles lie in some bigger representation of the global symmetry group than the fundamental.
Yes.
But this large n argument is not enough.
Yes.
Correct.
Yes. That's precisely true. So basically, here the starting point is not the Lagrangian. The way we should think is we have a model that we notice is integral. How? We did an experiment, right? So we scattered particles and we saw that the set of momenta initial and final was the same. So now we know it's integral, right? Then we also know particles transforming the vector, and there are n types of particles. And now we want to ask, given that, what is this tensor here within this IJAL? So, and we don't know the relation between this object and Lagrangian. It's a bonus, but we are never going to use the Lagrangian for anything. We are going to follow Zamolodchikov and compute this option. Any question? So that's where we are. Leandro, is it clear?
More or less clearly.
But is this part familiar? So what I said is that this is a model where if you scatter initial particles, the final state needs to be the same because you have conservation laws. That implies that the scattering factorizes, so the scattering of 4 particles is a sequence of 2 body scatterings into 4 particles in the future. And that means that all you need to do is the fundamental block, which is the 2 to 2 scattering, because everything becomes product of 2 to 2. And 2 to 2 is not any tensor, because it needs to obey a consistency condition that scattering in this order must be the same as scattering in this order. And that gives a cubic equation that should be very powerful to fix this tensor. Okay?
Something like you minimize the action with respect to the Lagrangian multiplier.
Right. I vary with respect to the Lagrangian multiplier.
But why does it help? Why I don't follow the logic?
The idea was that n was large. When n is large, you have the right to go to the saddle point. Because n is large, so it suppresses fluctuations.
But if you see in the action, the way to minimize the action is put n normalized to 1. So
N is not a field for which I have the right to use saddle point.
okay.
Because n, there is no sense in which n is dominated by saddle point. N is a quantum field. Lambda is dominated by saddle point, that's what we derived here. So the fact that lambda couples to n scalars makes lambda feel a very big background, and therefore lambda becomes classical. N no. So n is not classical, lambda is. Okay. Okay, so what out of all this, let's erase everything except what we need. So we don't care about equations of motion. We care about fixing this tensor. So and let's see what do we know about this. We know the model is integral. That why? Because we did an experiment and we saw that the initial and final set of momenta was the same. We know particles transform in the vector representation. Why? Because we just saw through Lagrange or the experimentalist told us. And so we have these particles all with the same mass, small m. And let's also impose, that's also true at Lagrange, where this particle becomes just free, that there are no other particles. In particular, there are no bound states. And let's also impose our theory is relativistic. And the claim is that if you impose all this, we can find this tensor. That's really impressive, right? That's all you impose. Yeah.
Will it be any
No bound state. Yeah.
So this will become, this will show up in the derivation. It will be the statement that this object does not have poles. Because we saw also in one of the courses that poles are bound states. For example, in the mesons, right, in the 4-point functional mesons, all the poles were the stable mesons. So if we had many poles, it would be the many stable particles. Here, we say there are no bound states. We have just these particles of mass m, but two of them don't form bound states. That was not obvious. Maybe they did, right? Because they were free at large m, but maybe when you turn on non-invariant corrections, they start forming weakly coupled bound states and so on. But if you want, that's an assumption. There are no bound states. It's the truth. It's correct. But for now, it will be experimental. I compute the spectrum and I see nothing, then m, and then a continuum at 2m. So that's what our experimentalist gave us. And this m, there was degeneracy g. Right? So there was this experimental spectrum, and integrability, and the theory is relativistic, because the world is relativistic. So now I want to compute, knowing this. So this is the gift that my experimentalist gave me. My gift back is I will give him the prediction to all the experiments possible in the test. Which is quite impressive, right? Okay, so let's do it. So the first thing we do is parameterize the momenta of these particles in a clever way. We write P1 as the mass and P2 as the mass times cosh of theta 1 sinh of theta 1, which is equal to energy of particle 1, momentum of particle 1. So you see that automatically it is on show. And P2, the same with theta 2. Well, then you can easily check that if you compute S, which is the same S that we saw in Landau's lecture, P1 plus P2 squared, which is the center of mass square of the process, which is the Lorentz invariant, the only thing that it could depend on, that this object is equal to 4m squared cos squared of theta over 2, where theta is theta 1 minus theta 2. So what happens here? What happens here is that my S matrix is only a function of the difference of rapidities. Is that obvious? How will I see that this has to be the case? Well, we computed, so we saw, but how could we have anticipated that that was obvious, that it was just a function of difference of rapidities? What's the definition of a rapidity?
Angle between the line doesn't matter
parallel transport.
using a capacitor.
You are doing something? Parallel transport is not the word I would use. What do we do in relativity? What interesting transformations do we do in relativity? Boosts? What happens under a boost to rapidities of particles? So if I have a particle at rest, theta is 0, right? You agree? What happens when I boost a particle? Under boosts, the rapidity gets shifted by a constant. That's the definition of rapidity. And the fact that it is Lorentz invariant must be independent on the shifting by rapidity, so it must depend only on the difference.
Must be independent if you shift
Under the shift of everyone.
everyone. Yeah.
Okay, so this is indeed relativistic invariant. We could have anticipated because boosts just shift these things. Notice that the non-relativistic non-relativistic limit corresponds, as the homological explains, to very small theta, where you just identify theta with the velocity of the particle. Right? Then this becomes velocity, and this becomes m plus velocity squared over 2, which is the kinetic term. Okay. So now we made progress, because now we have a function s. It still has indices I, j, k, l, but at least it's just a function of a single variable theta. Now, as a function of theta, what do we expect in the complex plane? Let's remember, what do we expect in terms of S? In terms of S, the center of mass energy, like we said, we have no bound states, and so all we expect is a cut that starts at 4m squared and goes to infinity. This would be this cut here. But similarly, in the T channel, there will be a process where I cut not in the S channel but in the T channel. And now I will get the T channel cut where T is bigger than 4m squared instead of S. So you could also compute T, and if you compute T, you find that T is just S at value I pi minus theta. Does it make sense? Let's see that it makes sense. Why does it make sense? Because looking at T is like flipping this particle, thinking of this particle as incoming and this particle as outgoing. But we send particle to antiparticle precisely when we do theta goes to I pi minus theta, where this energy is fixed and this momentum is fixed. Okay. But anyway, if I did not know, I would just compute T1 plus T4 squared, and that would give me T, and I see that T is I pi minus theta. And this is also equal to 4m squared minus S. So when there is a cut at T bigger than 4, means there is a cut at S bigger than 0, smaller than 0. So there is also a cut in the S plane at 0 going negative. So this is the S cut, and this is the T channel cut. So that's my expectation for the as an analytical function of S. It has S cuts and T cuts. Because these variables are not independent. S and T, they are just the same. T is just 4m squared minus S. If there were bound states, there would be a bunch of poles here. The pole and the cross pole. The pole and the cross pole. Bound state would be here. But here there's nothing because there are no bound states. So no poles there to be expected. Right? So nothing here. Don't be confused that you could think, why don't I see m, the particle? That's because in the product of two vectors, or say if I have a vi and a vj, there is no vector, right? I cannot construct a vector, a particle in the vector representation by multiplying two vectors. So in the scattering of vector with vector, there's no vector. Right? So the fundamental particle is not here. It's the same as when we have Z2 symmetry. And I scatter two odd particles, I cannot see an odd particle in the middle, only even particles. So here, there could be particles, but they needed to be in other representations of SOM, like symmetric and so on. But there are no, and so there's nothing here. Now, this variable theta is very nice because it will map all this thing here is called the physical sheet for obvious reasons. It's the complex plane minus these cuts. And this, in theta, is mapped to a strip. This is I pi, this is 0, and this is mapped to this, which is called the physical strip. So let's see how it works. So let's look at this map and see. So let's do theta positive. Theta positive means S bigger than 4. So this part here, S on top of the cut, is mapped to this part here. Right? What about this part here? That's also S positive. That's mapped to this part here. So you see, it opens up. It opened up this region. It resolved the square root. So it opened up nicely. Then we have this region here, and say this region here. And this, you see that crossing is the transformation. Theta goes to I pi minus theta, or S goes to 4m squared minus S. So it's a reflection around this point I pi over 2. So crossing would send this cut to this cut, and that's a reflection around this point. So this solid line is mapped to this dashed line, and this would be the wiggly line. All this you can just check that if I map this theta inside that strip with this map, that you cover the full complex plane minus these cuts in this way here. So let's just be more, let's just draw a line. For example, if I draw this line here, this would be something like this. I start here, and I go here, and I do something. I pass to the left of this point, this would be something like this. Okay? So we have a function that is in a strip, right? So we are after here a function that has no singularities inside a strip. What about if I analytically continue outside? Oh, it's full of singularities. In the same way that here, if I go inside these cuts in the other sheets, hell breaks loose. There will be lots of resonances and singularities, there will be hell there. Here as well. But inside the strip, no, it should be a beautiful function without singularities. So now, here it is, we have to find our tensor, where the entries are functions that are analytic in a strip. That's where we are right now. Any question?
I just lost how the single poles, they condensate pressure on the pi.
There are no poles, like I said. There are no bound states. No bound states means no poles here, and therefore no poles there. If you had bound states, they would be here between 0 and 4m squared, which means they would be here between 0 and I pi. But there are no poles, so the function is meromorphic in the strip. No singularities. Okay. Okay. So now, let's find this function. So now the goal is to, now let's use group theory to reduce computing all these elements of this tensor, naive that there are many, right? Because there are many indices I, j, k, l. Let's reduce it as homological terms to 3 functions, right? f1, f2, and f3. So what do? We write as I, j, KL equal. Well, let me follow his notation and factorize one function that he calls sigma 2 of theta. Sigma 2 of theta will multiply the tensor structure where particles I moves directly to L and J moves directly to K, the case of the free theory. So in that case, I would write this, where this would be index delta IL delta JK. This is one of the tensor structures I could write. One of the ways of contracting the indices that's multiplied by sigma 2. Another structure I could write is, I could say that I connect indices IJ and KL. That would be a process like this. In pictures. And that I have to introduce a function, let me call it 1 over g of theta. And finally, there is another process, which is when the indices are like this, for the particles, where they bounce back. So this would be annihilation, transmission, and reflection, where delta I is equal to K, delta J is equal to L, and the function I call it 1 over h of theta. That's just my choice of functions. It's a slightly different notation. Homological calls it sigma 1, sigma 2, sigma 3. So, but I just say let sigma 2 be the 1, I factor out, and then this comes with 1, g, and h. Okay? So, at this point, we need to fix, our goal is to fix 3 functions. Which are meromorphic in the theta strip. So we need to fix these 3 functions, h, g, and sigma 2.
It should be only seen as like the tensor structure, not that you're just doing free propagation.
Right, these are all the possible SON invariant tensors. If I have 4 indices, I need to contract them. The only thing I have is Kronecker delta. So what else could I do? I can only do this. But this is equivalent, if you want, in more group theory language. I could also write this same equation by saying that S as a tensor is equal to some function times the projector into the singlet representation, because 2 vectors can form a singlet, plus another function of theta times the projector into the antisymmetric representation, plus another function of theta times the projector into the symmetric traceless representation. This would be the 3 tensors that I can get. And then these 3 functions, f1, f2, and f3, would be linear combinations of these 3 functions here. Right? So this is just a notation, index-free version of that. But it's of course exactly the same thing. The fact that 2 vectors form these 3 representations is the same as saying that with these indices I can form 3 structures.
So
yes?
you're basically saying that if you have those bound states, the only thing as measures could be is annihilation.
No, that was not related to having bound states. That was just related to writing things properly with the index, with the good transformations under SON. We are studying a problem where we have n particles that transform nicely under each other. So if you have to write a tensor that has indices I, J, K, L, what can you write? The only tensors you have are Kronecker deltas. So you just write all these ways of contracting the indices.
Even with bound states, these work.
Yeah, even with bound states it will be the same.
The fact that there are no bound states.
The fact that you have no bound state is this, meromorphic. If it was not, it would be 3 functions which are meromorphic in the theta strip up to 1 pole in G, because there is 1 particle which is a single. Then it will be a very minor modification. But now they need to be meromorphic. Ah, okay, then holomorphic.
Yeah.
Yeah, I never know analytic.
Is it more complicated? More complicated computer if you have bound states.
No, it's the same.
But it's your choice.
Yeah, if I put bound states, I have to tell what bound states, what representation, where articles, it will be a mess. I mean, we'll spend 1 hour just to keep track of all that. Okay. So now we have to fix these functions, right? And now that's where we are going to impose the key things that we did not impose yet: integrability and relativistic invariance. So let's now impose integrability. Let's impose that scattering in two different orders needs to be the same for consistency of the theory. So if I consider a scattering in this order, that must be the same as scattering in this other order. Now let's try to use this. So here is where we are going to use that n is bigger or equal than 3. It's at this point here. So I'm going to use colors to say what particles do I want to scatter. So let's do a first scattering experiment where we scatter particles which are, for example, this color, then white, and then red. That's the initial state. And the final state, let's say red, I want to be here. No, I already messed up. I want this to be this one, and I want yellow to be here, and white to be here. So this is the process I want to study. This amplitude for scattering of the yellow, white, red to red, yellow, white. Okay. So let's see. So the claim is that let's try to follow the color. How could this white end up there, and this yellow end up there, and the red end up there? Using these possible structures: annihilation, transmission, or reflection. So, can you see what I want? Can you see what needs to happen here? For example, the red. Can the red continue?
Yes.
Naively, yes, right? Because it could continue and then bounce back and go there. But if it does that, how is the white going to get there? It's not. So it cannot. The only thing the white cannot lose time. It needs to bend right away. And then right? That's the only process. And then the yellow needs to go here and reflect here. And the red needs to go here and here. So that's the only process. Now let's draw it on this side. Red here. Yellow and white. What about here? What can the red do first? Well, the red again needs to go there. There's no way out. What about the white? So the white, does it need to turn or can it continue?
Both.
Both. Now it can do both. So one option is this. But there is another term, plus, we need to draw the other procedure, where the white does this part. Right? And the yellow does this. And the red does this. You agree? Now let's translate this into equations. So, let's translate this into equations. Let's say that this particle is with some rapidity theta. This one is at rest, let's put 0. And this one is with some rapidity moving in this direction minus theta prime. Then, this equation, there are always three scattering processes that I can factorize, which is sigma 2 of theta times sigma 2 of theta prime times sigma 2 of theta plus theta prime. This is boring. It is just that each factor contains a sigma 2 and it always appears 3 times because sigma 2 is factorized. So this is totally irrelevant. I just put it here outside. And now let's look as if there was no sigma 2 here. We just look at this inside here. And whenever there is a transmission, we put nothing. When there is an annihilation, we put a G. And when there is a reflection, we put an H. So let's look at the first term here. We have a reflection with difference theta minus theta prime. So we get a reflection 1 over H of theta prime from this. Then here we get a transmission, so nothing. And here we get another reflection 1 over H with the difference of rapidities, which is theta. Right? So this was 0 minus theta prime, and this was theta minus 0. Do you agree? Did you see this going to this? Is it clear? No, that would be this process here. The slope of the line is related to the rapidity here, right? So this is this. Then this term is this. And this one would be 1. Right? Because it's transmission. Okay. This must be equal, so we'll subtract and put 0. Now the first one here. Let's see now this one here. Transmission, so we put nothing. And then we have 2 reflections. One reflection gives 1 over H of theta plus theta prime. We always do bottom to top. And the other gives 1 over H of theta prime, the top one. Do you see? Do you agree? And the other one is minus this one here, the first reflection H of theta, the second reflection H of theta plus theta prime. Right? And so we conclude that H of theta plus theta prime is equal to H of theta plus H of theta prime. What is H? A linear function. That's the definition of a linear function. That implies that H of theta is equal to alpha times theta. That's quite impressive, right? H of theta is alpha times theta. Okay. That was one experiment we did. So let's do another one. So we already fixed one function up to one constant. Right? So we had to fix 3 functions, and we already fixed H of theta equal to alpha times theta. And you see it's meromorphic in the strip, no singularity. Okay? Well, sorry, I take it back. Here, it's 1 over H. So this has a singularity at theta equal to 0. So we better have this sigma 2 have a 0 there. But okay, it's almost singularity free. Right? So later we will say that sigma 2 needs a 0 at theta equal to 0.
So, which means indeed the 3 functions are meromorphic.
Yeah. Yeah, but by functions I mean this one, the coefficients of it. This has more information, right? Okay. So now we still need G and sigma 2. So the other experiment I want to do, I scatter the following. I scatter, how do I describe this? I can do like this. White, white, and yellow. Going into yellow here, red and red. Another experiment I can consider. Okay? So now we have to think, how can I do this? How can those reds go there? Okay, so how can I produce this red? So it means I need to produce colors eventually at some point. So could I produce it here? No, because these colors are different, there's no annihilation. So I need to produce it here. So the diagram for this, here it needs to have some pH for sure. Now what about down here? Is there any option or is everything fixed? So the yellow needs to go here. Can it do anything except turn? Let's see. It could. So there are two options. One option is it turns. Then if it turns, the rest is totally fixed. The rest is there is a reflection and there is an annihilation and a transmission. Right? But there is another process, which is, so the red is always the same, but the yellow, instead of reflecting, could continue, that's fine, and it could annihilate here, and then reflect here. And the white would transmit here, and annihilate. So that's also a possible process. And that's it with this ordering of lines. And what about the other ordering, where I put the ordering like this? Let's try it again. Yellow is this middle, and this. Red is this, and the other ones are white. How many possibilities are there now? Only one indeed, because the red needs to do this, clearly, right? That's the only way. And then that means the white needs to do this, and the yellow needs to do this. So it's only one possibility. Okay, so let's translate this now into an equation. So the equation now from this will tell me that 0 is equal to, let's do say let's do this one here. Again, this is theta, this is 0, this is minus theta prime. So I start with a reflection, so 1 over h of theta. Then transmission, it's nothing, and then 1 annihilation, 1 over g of theta prime. Then I have plus the next one, first a transmission, that's nothing, then an annihilation, 1 over g of theta plus theta prime, and then another annihilation, 1 over g of theta prime. Right? You see, the slope here is 0 and theta prime. Right? 0 and theta prime. And this minus the last term, which has first the transmission, nothing, then 1 over an annihilation at theta plus theta prime, and then a reflection at 1 over h at this and this, which is theta. Correct? Do you agree? Let me put the argument here. This argument is theta, and this argument is theta prime. This one is nothing. Then in the second equation, this is nothing. This argument is theta plus theta prime, and this argument is theta prime. And in the last equation, this is nothing, there's a transmission, and this one is theta plus theta prime, and the last one is theta. Right? 0 and theta. Okay? So the equation is okay. And so now this equation implies what? This equation implies, if I multiply everything by all these denominators, it implies that first term is g of theta plus theta prime. The last term is minus g of theta. And I put the one with h on the other side is equal to minus h of theta. Here it's theta prime. And minus h of theta is minus alpha times theta. So what is g? In the same way that that's the definition of a linear function, what about g? Almost?
Plus a theta squared.
Plus a constant. That's the definition of an affine function. Okay? Very good. And so, g of theta is minus alpha theta plus beta. Right? So at this point, we need to fix, let me correct here, one function and two constants. Right? That's where we are. We need to fix beta, we need to fix alpha, and we need to fix sigma 2. Now, sigma 2, forget about Young-Baxter, because Young-Baxter in its factorization, sigma 2 is always outside. So sigma 2 is this is never going to help. But Young-Baxter, there is one more experiment we could do, but that equation has 8 terms instead of 3. So I'm not going to write, I'm going to tell you the colors of the experiment. If you do the experiment with the following colors, which is this, and then this, and then the red, you put here the 2 red. So now here there are many possibilities. The reds can annihilate, this can annihilate, this can reflect, there are many terms. And this will give, this choice of colors will give 7 terms equal to 1 term. So one ordering, there's one option, but the other option there are 7 terms. So you write an equation, instead of 3 terms, there will be 8 terms in total. One of these terms here will contain a color loop. So there will be an explicit factor of n in one of the 7 terms here. It will be possible to create a 4th color. That was something we could never do there. And so, this now, what this equation will do is it will fix this beta to be 1 minus n over 2. Okay, that's what this last equation does. And that's it. It cannot do more. Because it can never fix alpha. Because there is an obvious symmetry that if I rescale all rapidities by alpha, it's also a solution. So this is as much as Young-Baxter could do. You did 3 experiments. Now you could be worried that other experiments could contradict what you found, but they don't. And so this is good. You can now check that it obeys for any choice of color that now it obeys if beta takes this value. Okay. Okay. Sorry? Right. So now at this point, we have one constant to fix, alpha, and one function. Okay. Now, let's use relativistic invariance. Relativistic invariance tells me that this relativistic invariant tells me that sigma 2 of theta is equal to sigma 2 of I pi minus theta, and sigma 1 of theta is equal to sigma 3 of I pi minus theta. Let me explain this. And the reason is the following, is that these transformations are just swapping S and T. Right? So these transformations here are just swapping S and T. But let's look at these tensors. If I swap time and space, what happens? This tensor is invariant. Looking at it like this or like this is the same thing. So this coefficient of this tensor should be invariant under crossing symmetry. But this tensor becomes this and vice versa, and this becomes this. And so under crossing symmetry, this function should become this function. Okay? And so that means that h of theta should be g of I pi minus theta. And this fixes alpha. Okay? So now this fixes alpha. If I put here I pi minus theta, I must get this function. Right? So it tells me that this alpha is equal to beta over pi, something like that, right? Beta over I pi. Right? Such that when I plug here I pi minus theta, the I pi cancels that, and I get the beta, and the minus gives this term. Okay? So it fixed beta, alpha to be this. And now, finally, we need to fix. So now we just need to find sigma 2 of theta. But at this point, let me emphasize how remarkable it is what we did already. You see that now, imagine you are doing an experiment, right? And you do any scattering experiment at some energy, divided by the same scattering another scattering experiment at the same energy. Sigma 2 would cancel, and you are already predicting the ratio between all physical processes. Right? You are saying if I scatter these colors versus these other colors, you predict all the ratios of all possible amplitudes, right? It's quite remarkable, right? It's all up to one single function that we need to fix. But otherwise, all processes are fixed up to one overall function. And now this sigma 2, what do we know? We know sigma 2 obeys the equation. Sigma 2 of I pi minus theta equal to sigma 2 of theta. And the last equation we have to impose is unitarity, which is the condition that S dagger S is equal to the identity. Right? That's the crucial equation we didn't impose yet. So what is S dagger S? It's just applying S twice. So in equations, that's just this picture, that if I multiply two objects, I get the identity. So I just take an S matrix, scatter twice, first with theta, then with minus theta. Right? I'm using that this S dagger of theta is basically S of minus theta by CPT. And so I just take S of minus theta, I multiply two such tensors, and I get an equation that will be sigma 2 of theta times sigma 2 of minus theta, that's the overall factor, is equal to some factor of the form theta squared over theta squared plus some beta square, I believe. Okay? So this is the scalar part that is in front, the contraction of the matrix, etc. Put equal to 1, but then I put a matrix on the other side and I get it. And so we are left with finding one function that's meromorphic and that obeys these two equations. Again, this one is crossing symmetry, and this one is unitary. And I'm probably over time, so I'll just tell you, but if I'm not over time, I can explain a little bit, that this implies that this fixes sigma 2 completely. And basically, it will give that sigma 2 is a bunch of gamma functions. You can write it as a simple infinite product of gamma functions. It's not totally trivial, but it's very expensive. So that's it. So that's the solution of a fully strongly coupled to the quantum field theory, where we just compute completely sigma 2 of theta. We already compute the H and G, so we know completely the two body S matrix, so we know the n body S matrix, so now we can predict the outcome of any scattering experiment in the field. That's really impressive, and the key thing was relativistic invariance. That was a very powerful extra constraint. Up to this point, everything was true also non-relativistic, and people already knew some of these equations. But then, this relativistic invariance was really very powerful to be able to close a set of equations. Without it, you would be left only with the last equation. But the last equation is not very powerful. It's not enough. So relativistic invariance, it's a minor thing, that's the title of the paper, but that's what really gave you the power to fix everything. Without relativistic invariance, we would have two constants to fix instead of no constants. Sorry, we would have one constant to fix, alpha would not be fixed. Right? So let's recap. So without relativistic invariance, we don't have, so when it's non-relativistic, we don't have this equation. And then this equation, alpha would still be here. There would be an extra parameter here. So we would have only one equation with one parameter, instead of two equations with zero parameters. So two equations without parameters, we have a full solution. One equation without parameters, we have many solutions. And that's fine, because when you don't have relativistic invariance, you have quantum mechanics, and there are many quantum mechanics integral theories you could write, and many modifications, and the structure is much less rigid. When you put in relativistic invariance and absence of bound states, you really constrain enormously your model, and you solve it uniquely. And what Homologikov does is he shows that you can do it not only for this ON model, but also for other interesting integral models. Now, when you solve it, it's quite impressive that you get all these gamma functions, but then how do you know this is a good solution? Because everything is non-perturbative, strongly coupled, and now what do you do? How do you know it's correct? How do you know you did not screw up, or you didn't forget, or maybe your assumption of no bound states was wrong, or...
You can check with multi-particle scattering. You could check.
But what would you check? Against what?
For instance, there we had three particles scattering into other three. We could get four particles and see if we could.
But how would you do that computation of the four particles?
Okay.
The theory is strongly coupled, so you cannot use Lagrangians to compute. If you assume it factorizes, then you are assuming what we input. Then, of course, it's going to work. It's not a consistency check. Very good. And what is that somehow? How could we retrieve perturbation theory if the theory is not weakly coupled? Like I said, there's no parameter, right? The equation is just del n squared plus large n. Because now you see, if we expand that large n, what happens at large n, this beta is huge, this G goes to 0, things simplify. And what you will see is that the S matrix will become just the identity. Plus corrections, because that's what we expect, the period should be free. So when we expand at Largenia, what you will see is that G and H go to 0, because you see beta goes to infinity, alpha goes to infinity, so H and G go to infinity. So these two terms disappear, and the S matrix becomes proportional to this term. And if I gave you sigma 2, you would see sigma 2 would go to 1. And so the full S matrix is 1 plus a small correction in 1 over n. So now we could try to develop an expansion in 1 over n by keeping the saddle point computation we did more carefully with fluctuations and so on. And that's one of the things he did. He carried out the 1 over n expansion carefully a few terms and compared it with the 1 over n expansion of this exact result. And then it works, the first 1 or 2 terms that he computed. So that's one check you could do. And then there are other checks, more sophisticated ones, but that's what we are going to explain on Friday. But that would be the check that he did in the paper. Okay, so I think, how much time did I use? 3 o'clock, so 1 hour and a half. Yeah, so I went 25 minutes over time. Okay, so let's see who is presenting next week. We can stop the recording. No, we can keep. It's okay. We don't have an adapter, but that's irrelevant. So I was going to ask Rodrigo if he was here, if he wanted or not to present next week. Ele quer apresentar na próxima semana ou ele prefere apresentar na outra? Porque ele só tem uma apresentação. Então, eu ia colocar o Leandro na próxima semana sem dúvida. Agora, se punha o Rodrigo ou não, é-me indiferente. Ou ponho o Leandro e o Rodrigo, e aí ambos ficam com duas. Sorry, I put Leandro and Rodrigo, both will have 2 presentations. And then, was I speaking in English or Portuguese before? I was just worried that Naki and Connor might have suffered through 1 hour. Good. So, Leandro, yes, but otherwise, Rodrigo, I don't know if I will put or not, so let me put here. Leandro. So, who else is in the... Should I randomize for next week? So, that did not present... Who else did not present last time? This Friday, yeah. Sorry, this Friday. Who did not present last Friday? So, Alan, Dennis. So, if I said your name, you can lower your hand, otherwise keep it up. Alan, Dennis. Gabriel, you presented? No.
Sorry.
Gabriel, Rodrigo, Aguiar. Okay, so I have 5 people here. What do you guys think? Do I put Rodrigo Aguiar and randomly select 2 out of the other 4, or do I select 3 out of these 5? Normally I would suggest to put Rodrigo, but I feel a bit bad that he did not come to the lecture. It could be tough for him, no?
I can try to ask him, but
Is he online?
I don't know, maybe not currently.
So let's do the following. Let's assume Rodrigo presents and select 2 people. And then we'll select 1 more that will check with Rodrigo and you guys decide, either Rodrigo or the other one. Okay, so here are the 4 people. Right? So Leandro, Alan, Dennis, and Gabriel. I took out Rodrigo and I will select 2 of those. Okay. Oh, no, I did not run this. I run. So Dennis and Alan will present next week. So, and then now let me do random integer from 1 to 4. Leandro, now I will randomize when you will present. So you will be the last one next week. And let me select a random integer from 1 to 3. Rodrigo Aguiar will be the third one. And so we will have Dennis, then Alan, then Rodrigo Aguiar, and then Leandro. But let's select now finally. In case Rodrigo Aguiar doesn't want to present next week.
If you want to present, you can present. I asked him.
He
Confirmed that he can present.
okay. Let me still randomly select. Just imagine the recording doesn't work, and then he doesn't have the recording. I think it could be too tough, no? I don't know. Maybe he already studied the paper and found it was easy, but I don't know. I feel. So let me remove Dennis and Alan and select one out of these two. So Gabriel will replace Rodrigo Aguiar if Rodrigo cannot. So this is okay. If Rodrigo can do it, otherwise Gabriel will do it in this session. So that's the setup for Friday. And we do Friday at 9:30 or at 10. What do you prefer? Doesn't matter. Let's do 10. Okay. Yeah. Okay.
So, you can present it. Do you have some recommendations? Because I have not yet.
Maybe for some options, send me and I got out of these three, this one will tell us.
Okay. Thank you.
But in principle, I think Rodrigo should be okay. But let's see. Yeah. There are some, for example, the gross multiple model, which also has a symmetry and so on, goes through exactly the same except that it's one bound state. And so in the step where you need to solve these equations, you will need to impose at least one pole. And so then you will get a bunch of ground functions times a pole. So it's simple to put bound state. It only appears in this very last step when you solve those two equations.
But if you have many more states, or finitely many bound states, then you can have
Finitely many bound states. But for example, you see that bound states transform into some representation, right? So a bound state is a pole in one of these representations. Right? So you could ask, can I have 5 bound states in the symmetric representation? Probably not. Because it's not up to you to decide to put a factor here and not put it here, because all the ratios are fixed. So that would mean there's no integrable theory which has 5 symmetric bound state poles. So maybe we'll find out that you can put one bound state in symmetric if you also put in singlet, perhaps. And you might not need to put in all, but you will probably need to tune them a little bit. It's not up to you to decide what to put. So then there is a study of, if you did not know where the bound states are, can I look for solutions where it admits bound states? And then there is a bootstrap program to fix the location of the bound states so that this is consistent. Because you cannot do whatever you want because the relative weight is fixed. So you can't put poles here and not put here. Right? The two functions differ by theta. So if one is poles, the other is poles.
So is this condition that it meets a zero at theta, is it ingrained in finding this sequence of zero, or?
Yes. You see that this equation tells me that the right hand side is 0 at t equals 0. So it's great. So this equation where you must write sigma 2 to be 0 at theta.
Sorry.
This equation also tells you there is a pole at theta equal to I beta. But where is the pole? Is that I beta or minus I beta? Because you have two factors here. So let's suppose you have no bound state, then it should be at minus I beta. Then you put a pole there. But then you look at this equation and it says that if it has a pole there, there's a pole here. Then you go here and you say if there's a pole there, this is reflected, there's a 0 here. Then you find a 0 here. A 0 here implies a 0 there. Then there's a 0 there. I go here, there's a pole. And I start doing this game and I start learning that my function has an infinite number of poles and zeros that never stops. On what functions have many poles and zeros? Gamma functions. So then I just make a list of allocations and I guess right away, oh, it's a bunch of gamma functions. And that's how you solve the equation. So you start guessing about poles and zeros by looking at the equation. Yeah, it's the beginning of the It's cute, huh?
It is, yes.
It's kind of a luxury that we can, not every day, we can solve something. Sorry? Alguma sugestão? Tanto paper, isso é normal. Ver os papers que sigam. Se você quiser, passa aqui uma hora, ou seja, Gonçalo, se tiver alguma sugestão, se tiver alguma, mas assim, paper muito recente.
Eu achei difícil. A maioria era seu, né? Tinha vários papers que eu pensei em outras 50.
Esse foi bom? Pode.
Sim, foram bons.
Mas
Tem um só que eu achei interessante.
Eles vão explicar como é que os métodos normais, eu trouxe para aqui. Não conheço esse paper. Quantas citações tem?
Eu falo de 30 para mim.
30, 40, 10 anos? Mas não é interessante, mas eu queria ver como é que dá. Como eu disse, envie duas ou três escolhas.
Foi uma coisa.
Essa é uma possibilidade, sim. Não é óbvio que seja uma má ideia, mas não é um paper assim muito original. É só como é que eu faço diagrama de Feynman e vejo que nos diagramas bate certo com integrabilidade. Uma teoria que eu tenho um diagrama de Feynman, ok, isto vai funcionar. Como é que pode não? É um pouco. É um exercício. Se eu tiver uma teoria que é integrável, mas tem um coupling, não é o caso. Essa não tem coupling, é só um coupling. Não há parâmetro nenhum. Se eu não tenho parâmetro nenhum, o coupling que havia passou para a massa da partícula. Então passou tudo a ser massa física. Esta é massa não perturbativa. É o equivalente à massa da globo, assim, é não perturbativa. Calculou a massa e tudo vem em termos da massa. O coupling desapareceu. Isso é o que se chama dynamical mass transmutation. Então não tem coupling. Quando tem coupling, algumas teorias são integráveis e tem coupling ainda. Então tem um parâmetro que pode brincar para ficar livre. E aí pode expandir em torno da teoria livre e ver que está a mesma coisa que a teoria de ultrapassar. Isso é o que esse paper faz. Verificar se a teoria tem um weak coupling, o weak coupling da solução exata dá a solução perturbativa.
E seria um sobre.
Neste caso é um sobre. Mas noutras teorias pode ter mesmo um parâmetro de acoplamento que sobrevive, que não desaparece. Pode ter uma teoria que tem um coupling. Você desliga o coupling, está livre. Desliga o coupling, tem interações. Existem alguns casos sem borda, não é um caso. aqui é a equação cúbica, né? Foi SSS igual a SSS. Essa é que é a equação bem poderosa, né? Que dá para... Então, há muitos papers que, se o paper tem esse tipo de figura, como estes diagramas triangulares, tem alguma coisa a ver com esse paper. É, SSS igual a SSS. Isso aparece em muitos contextos. Então, muitas teorias, o pessoal tenta escrever essas equações e ver se funciona. É o ponto de partida. É uma equação super não trivial, é cúbica, não é muito forte. Né? Nós fixamos tudo, né? Temos assim equações super poderosas. Né? Então, o paper tem muitas citações, mas eu tentava focar nas que tiverem esta figura com esses diagramas. Se vocês me enviarem algumas sugestões, eu vou pensar mais e posso enviar mais também, posso também colocar no Google Classroom, se eu me lembrar. Mas é mais diferente, porque é algo que eu trabalho tanto, eu nem sei quais dessas receitas. Os outros assuntos, talvez.
Eu tentei
Eu sei mais.